Hi, and we are Tory Statistical Nerds. Today we'll be talking about random situations and how they relate to probabilities, and we'll also be diving into the law of large numbers. My name is Amanda Maharis.
I'm Yana Gunther.
And I'm Joseph. If you're told to randomly select a number from a given set, would you be able to do it? The common answer is yes. But what you hadn't taken into account is that humans do not have the ability to select anything with complete randomness. There's always something that a person derives from their mind, with or without intent, in which they use to make their decisions. Take this plot of 10 by 10 squares, for example. If I were to tell you to randomly choose 25 of these squares and fill them with color, how would you do it? We went to the field to discover the thing. We have John Muller here from the Sonoma State Library to help us with this task. John, would you please select 25 random squares and X which one of these were red? Thank you very much.
As we can see here, our experimental subject produced a diagonal pattern going through the diagonal portion of our plot, producing his own type of pattern.
Additionally, without meaning to, he actually uniformly distributed his x's without leaving any spaces.
And as you're watching the clip, you can see at one point he actually pauses and looks at one certain area where he completely was devoid of x's, and he just plots one right there in the middle.
And in an attempt to make randomization, he actually did a pattern clear sight, as you can see with these two rows.
And as we can see here, he also tried to compensate for the fact that he had not a single one of his x's originally touching another one of the x's. So he produced diagonal touching, as well as ones that were right next to each other, to try to produce a certain other form of randomness that in the same way kind of counteracts what he had already done.
Now let's really try to get something that's random. We're going to assign a number to each one of these boxes on the grid, and we're going to see what our calculator produces.
As we can see on this plot, a human makes a pattern even when he intends to produce randomness. Now let's see how the calculator does it with its program in its function menu.
And now for this portion of the segment, we have moved from to all off for.
And one way we can do this is going to Math, PRB, 5 to random integer, 1, 100 for the amount of numbers we can choose from, then 25 to produce 25 randomly generated numbers. Press it, and here are your 25 randomly generated numbers for us to put on our field. Same process can be found if you do Math PRB random integer again, but instead of having it 25 times, do 1, 100, 1, and then continue to pick up 25 numbers from this account. We have our 25 numbers now. Time to apply them for our plot.
64.
Amanda Maher is back with you. While you're watching my fellow partners exit out, I'm going to explain an additional situation. Given a piano has 52 keys. If we were to number each of those keys from left to right and generate 32 different numbers in our calculator program, what kind of music would that make? You will get to see in a short while. Thank you.
41, 29, 42, 71, 90, 84,
You now see in our 10 by 10 field, we have our 25 numbers plotted down, and you can see there's a real lack thereof of a pattern.
For example, there's a big empty space right in here, which a human most likely would naturally want to fill.
And also you can see there's so many spaces that are very, very close to each other in the number field that it would just kind of seem like you're making the pattern as you're making it if you're a human. We're getting our 25 numbers. What we originally wanted was 25 separate numbers that we could plot here on the field, but we did get the number 43 2 times. We get to compensate for this by adding an extra number. In the case we were talking about earlier with the piano, we actually can repeat numbers, and so it is truly more random.
So we were using a calculator to generate our numbers. However, a calculator's generation of numbers isn't completely random. It uses an equation to generate the numbers. However, it's as close as we're going to get, and it's far better than the human mind at generating random numbers.
We input the data from our piano situation that we addressed earlier into the equation that we have on our calculator with the random integer field. We have repeating numbers of 5, 36, and 46, just to name a few. It even has multiple 46s, you can see here, appearing 3 times in our number field.
Random integers can be used to simulate situations in which you want to find out the likelihood of an event happening. Let's do an example problem. So for this first problem, we're going to utilize the normal model, which hopefully you learned about earlier in the year. So here's the situation. A certain college estimates that the 3-score SAT total for students who apply for admissions can be described by a normal model with a mean of 1570 and a standard deviation of 180. Admission officers search the pile of envelopes, opening them at random to look for 3 applicants with SAT totals over 1,800. How many envelopes do you think we will need to open? Let's find out. So let's first draw a normal model with a mean of 1570 and a standard deviation of 180. Okay, so now we'll find the z-score of 1,800. To do this, we'll use our ZDMS formula in which z equals c, which is datum, minus mean, over standard deviation. So in this case, it is 1,800
minus 1570 over 180. So we calculated that, and we got 1.2778. Okay, now we'll use NCDS to find the probability that an envelope that we take is over 1800.
So to get the normal CDS, we go to second distribution down to normal CDS, and the lower is 1.2778, which is the Z-score for 1800. Upper is 99, representing the right upper end of the normal model, and then we get 0.1007, which contextually is the probability that we will get an envelope with a score over 1800.
Okay, so we just did NCDS from 1.2778 to 99, which reflects the shaded area under our normal model. Okay, so next we assign numbers that reflect the probability of an event happening. So in this case, we'll choose 1 through 10 to represent the probability of opening envelopes over 1800, and 11 through 100 to represent the probability of opening envelopes under 1800. That reflects the 10% of envelopes that are over 1800. So next we set up our random integer on our calculator, and that is set up as RandInt 1, 100, 1. So next we need to run trials. A trial is a sequence of events that we're pretending will take place. We want to pretend that we're opening envelopes until we find 3 that are over 1800. Our response variable is what we're interested in. We want to know how many envelopes we have to open until we find 3 with scores over 1800. So we click generate random numbers on our calculator, and we'll mark down an X every time that we get a number over 10, and a circle every time we generate one under 10. We'll keep doing this until we have generated 3 circles, as these represent the envelopes that have scores over 1800, and the number of times that we generate numbers is how many envelopes we've opened. So we'll continue to run a couple trials and then average the outcomes of these trials to figure out how many envelopes we expect to open. So we'll run our first trial together. Remember, numbers 1 through 10 are represented by a circle, and 11 through 100 are represented by an X. So we'll set up the random integer, and we'll keep generating numbers until we get 3 circles, because these represent the 3 envelopes that we open that have scores over 1800. So our first number is 9, so that's a circle, 52, 45, 44, 14, 53, 53 again, 60, 41, 54, 31, 40, 48, 68, 86, 60, 48, 37, 19, 8, 77, 51, 5. So in the trial we just did, we got 23 envelopes. So then we did 9 more trials because we can't do just one. And we got 23 from this one, 42, 33, 51, 39, 15, 27, 30, 34, and 52 envelopes opened. And then we averaged those, and we got about 35.6 envelopes expected to open. But because we can't open 0.6 of an envelope, we'll round it to 36 envelopes. Close enough for CRP USD budgetary work. Now that we've run our trials, we can state our conclusion and context. We always start with the phrase based on our simulation because our results are only based on our simulation. We don't know that this will actually happen in reality. So, based on our simulation, we estimate that the admissions officers will need to open an average of 36 envelopes until they have found 3 that contain scores over 1800.
Amanda!
Hey, Rhonda.
Got a lottery ticket.
That's exciting.
I know, 50% chance of winning, right?
Wrong. Even my dead dog knows that.
Oh.
Yeah, in actuality, there's only 1 in 175 million chance of winning the jackpot. This is due to the probability of one getting the exact combination out of the millions and millions of possible combinations one could come up with in the actual drawing. Another logical fallacy relates to non-nerd statistics scholars at a casino playing roulette. If 27 black numbers came up in a row, one would think that would have to be red next, right? Wrong. There are 18 black spaces and the total 38 spaces. So the probability of the ball landing on black is 0.4737. There are also 18 red spaces out of the total 38 spaces, which is a probability of 0.4737 for picking a red space. Although we are not currently concerned about the probability of picking green, it would be 2 out of 38, or 0.0526. According to the law of large numbers, there's an equal chance of either red or black being the number the ball lands on, regardless of the previous color, because these events are independent. The spinner does not have a memory. It does not go, oh, I've been black for too long, I should be red now. Each spin has its own outcome, which does not affect the outcome of another spin. However, you might ask yourself, so how could that be? If 27 black numbers showed up in a row, and then a red, wouldn't that be 96.43% black and only 3.57% red? That differs from the expected outcome of 47.37% frequency. However, there are only 28 trials. Over time, the percentage of black and red colors appearing would equal their expected frequencies of 47.37%. Let's simulate this. Here we have a white bag similar to Hermione's, filled with an infinite amount of pieces of paper that possess the ratio 4 red to 3 blue to 2 white to 1 green. Thus, the probability of picking red is 4 out of 10, which equals 0.4. The probability of picking blue is 3 out of 10, which equals 0.3. The probability of picking white is 2 out of 10, which is 0.2. And the probability of picking green is 1 out of 10, or 0.1. Let's run some trials and plot our graph.
We repeated this task 99 more times and recorded the results in the following tables.
And graphs. This table indicates the percent red for each of our trials. As you can see, the first 9 trials is more than our expected value. However, in this graph, over time, once we reached our 100th trial, our percent red settled down and equaled our expected value. The percent blue for each trial was less than our expected value of 30%. In this graph, over time, it raised and reached our expected value of 30%. The percent white for each trial was more than our expected value. However, over time, it once again equated 20% due to the law of large numbers. Our final color, green, was originally slightly higher than our expected value, but over time it equated 10% due to the law of large numbers. I hope you have enjoyed our presentation regarding random situations and how they relate to the law of large numbers.
So what have we learned today? First, we learned that humans are not capable at randomly making decisions. Calculators and computer programs, although not perfect, are as close as we can get to randomness. And calculator programs can also be utilized to solve real-world problems or simulations.
Additionally, we learned about gamblers' fallacies, We learned roulette tables do not have memories. And independent events follow the law of large numbers. I'm Yana Gunther.
I'm Joseph Pearson.
And I'm Amanda Harris, and these are Tori Stats Nerds.